Hi everyone, my name is Phil Lambert. I am a Senior Applications Engineer at Fortify, and my tech talk is called Application Highlights, 3D Printing of Low-Loss RF Devices. Fortify is introducing a new palette of polymer dielectric materials for printing components used in high bandwidth, high frequency communication systems, bringing the ability to design and print low-loss GRIN lenses and other RF devices to a DLP platform. GRIN devices, gradient index of refraction devices, when printed with Fortify's low-loss photopolymer material systems, will unlock lenses that can operate over wider bandwidths with increased aperture efficiency, at higher gains, at a lighter weight, all in a scalable and cost-effective manufacturing process. Before we dig into 3D printing of low-loss materials, I want to talk a little bit about the current state of the art in GRIN devices. GRIN devices are not new. In fact, the Luneburg lens concept was first proposed in 1944. The limitations in these devices restricted widespread adoption. These limitations were things like manufacturing, ease of manufacturing, cost, and device performance. Historically, the primarily utilized bands for TV, radio, even early telecom 1G and 2G were low frequency when compared to the modern EM spectrum utilization that we're seeing today. And lower frequencies with much larger bandwidths would have made these devices huge, heavy, and completely impractical. As modern applications reach into higher bands and manufacturing technologies advance, GRIN devices transition out of obscurity and into cost-competitive practicality. In each manufacturing case shown here, the complexity of the device creates huge manufacturing bottlenecks. In some cases, you need to precision manufacture a multitude of shells or wedges and then assemble them without air gaps between each of the dielectric components. In other cases, such as a drilled and stacked dielectric laminate lens, the top right of the slide, you're drilling or molding hundreds of thousands of individual elements. In either case, the cost and time to manufacture any of these devices shown on the screen in these traditional manufacturing technologies is extremely high. There are some additive manufacturing approaches out there for GRIN devices. Through conversations with customers, review of academic publications, and reviewing what is commercially available in industry, there are a few technologies making headway in printing GRIN devices. These known approaches are fused filament fabrication or direct write technologies, material jetting such as polyjet, stereolithography, and digital light processing, often called DLP. When thinking about printing technologies and what materials make the most sense for RF devices, we think about this critical characteristic called loss. Dielectric loss, or energy loss from a signal due to dissipation in the dielectric material, can cause significant performance reductions, especially in monolithic RF focusing devices like lenses. Basically, to get high performance, we want this loss value to be as low as possible. When thinking about critical performance characteristic, this dissipation factor, photopolymers have always struggled to compete. Looking at this chart plotting the dielectric constant on the y-axis of a variety of 3D printable materials to their dissipation or loss factor on the x-axis, which is in a logarithmic scale, we can basically draw a line right down the center. To the right, where the materials have higher loss, you'll mostly find photopolymers. On the left, in the direction of the lower loss, you'll mostly find thermoplastics. These thermoplastic materials inherently exhibit lower loss characteristics. One note about this chart here is that the data presented is sourced from a few academic papers, so the test methods and test frequencies are not all identical. However, the samples in these academic papers were tested at 10 gigahertz or above, so these trends are consistent for these high frequency applications we're discussing. When thinking about the additive manufacturing trade-offs for the devices that are currently being manufactured through AM today, there are benefits and drawbacks for each of the technologies. Fused filament fabrication can leverage the naturally good electrical properties of thermoplastics, but extrusion technologies are bound to a tough trade-off between build speed and feature resolution. Material jetting, on the other hand, has the potential for high throughput with excellent feature resolution, but is limited again by those poor electrical properties of the photopolymers. SLA materials suffer from a similar fate as well, and also having some throughput challenges tied to the laser rastering times. The takeaway here is that existing additive manufacturing technologies may have great RF properties, excellent feature resolution, or high throughput, but they don't have all three. But now, with With the materials we are discussing today, the dielectrics are ready for the next generation of RF devices. These materials, which are heavily filled with RF ceramic additives, have carefully selected dielectric constants with impressively low dielectric loss tangents. The data presented here is captured and tested at 10 gigahertz. With this development, Fortify brings on two impressive material systems targeting high-resolution, low-loss devices. Revisiting this chart from the beginning of the presentation, we can see where these two low-loss photopolymer materials fall on the chart. These materials exhibit competitive loss performance when compared to both the thermoplastic fused film fabrication and SLS materials. This 4.9 material, which will continue to be in development for a few more months, breaks the paradigm of polymers living in the 2 to 4 dielectric constant space. This dielectric polymer offers incredible advantages when designing monolithic, high contrast refractive index devices. And all of this is made possible thanks to a technology at Fortify we call CKM, or continuous kinetic mixing. CKM is a fluid pumping and heating system which manages viscosity by circulating and heating the resin, which helps to eliminate particle settling by keeping all those particles suspended due to fluid flow and other mixing elements. This technology helps to preserve the consistent RF properties in all axes due to the homogeneity of the material. And it also helps us to print thin struts and bulky parts with equivalent consistency and ease without a reduction in any performance along any feature. If you want to hear more about CKM, you should check out the CKM Tech Talk. There's going to be a lot more information about the individual components of this system and of this technology in that Tech Talk. So we took this low-loss dielectric material and used it to make a test device. The material we used in this case was the 2.6 DK material to design a Luneburg-Style lens. We designed a 62 millimeter lens. It's composed of a core and 5 shells. The permittivity distribution as a function of 3D space is shown in the screenshot on the right. The image shows warmer colors towards the center, which represent a higher DK at the core, where the cooler colors on the surface are closer to the permittivity of 1.1 at the surface. So this lens, while it's designed to be Luneburg-like, it's not exactly a 1 to 2 DK lens. It's a 1.1 to 1.92 DK lens. And to convert this digital design from a theoretical permittivity distribution to a real part, we use lattices. So the Fortify platform can print these functionally graded architectures in the form of a lattice by generating monolithic components with smooth gradients of effective permittivity from one local region to another. The GRIN lens on the right was printed at Fortify on a flux core printer, then took this lens and mounted it to a fixture in front of an open-ended waveguide feed source, which was then affixed to the test rig in an anechoic chamber. The lens was illuminated at 25 to 32 gigahertz, and the beam patterns were measured. A similar lens device, which has not been shown on the screen, was manufactured as a point of comparison from a conventional photopolymer material with a 2.9 DK and a loss of 0.039. So through this exploration, we're seeing real performance improvements. The results are clear. The lower loss polymer performs at a higher level than the conventional photopolymer. The radiation patterns you're seeing here on the left of the screen show the comparative result between two lenses. The one I mentioned, manufactured from the conventional photopolymer material, is represented here by the red curve, while the low loss 2.6 DK material are shown in the green curve. And by using the low loss 2.6 dielectric material, we're able to recognize a 3 dBi gain and improvement over the conventional photopolymers. The lens was rotated in the mount relative to the feed source to evaluate the performance from several different feed positions. The intent here is to demonstrate one of the unique characteristics of a Luneburg lens, which is the ability to focus energy and form a beam from any position across the surface of the lens. The lens is rotated twice, once to 45 degrees and once to 90 degrees from the original position. The chart shows good agreement with one another for each position and each tested frequency. The chart on the left shows the 3D antenna pattern of the lens at 30 gigahertz. And the right chart shows the amazing wideband performance of the lens from 25 to 32 gigahertz. The gain increases as the wavelength decreases, which is due to the growing aperture without breaking down. The red curve on the chart also shows a lower performance of the traditional photopolymer across several frequency bands. This wideband performance is excellent for devices in the Ka band, making it an interesting and intriguing option for the 5G millimeter wave applications, as well as satellite communications or radar. The lens concept is also an interesting option when trying to reduce overall form factor and weight. When compared to two standard gain antennas in the Ka band, which are shown on the right, the 62 millimeter Luneburg lens can realize a similar gain in a much smaller form factor. Also, naturally, the photopolymer device, consisting mostly air, will weigh considerably less than either of these two metal standard gain horns. And even when comparing to other polymer devices, such as a 6-inch Rexolite hemispherical lens, a similar designed 6-inch photopolymer lens weighs more than 55% less when compared to the solid constant K dielectric lens. Those weight savings can mean a lot, especially for design engineers who are constantly battling size, weight, and power swap considerations. And finally, the manufacturing of this device, the manufacturing of this high-performance GRIN Luneburg-Style lens is truly scalable. Considering the parallelization capabilities of DLP, device throughput impressively accelerates as DLP cures entire cross-sections of a build plate in a single exposure using a projected UV light mask. 1 part or 5 parts will print at the same rate, providing that they can fit on the build platform. In the case of the 62 millimeter diameter Luneburg lens, we can fit 5 lenses on the build plate at a time. With a build time of about 15 hours, the throughput is roughly 3 hours per lens. Comparing to fused filament fabrication, which can take an estimated 12 hours to complete just one 62 millimeter lens, the Flux Core can produce 5 lenses in a quarter of the time. So thanks for checking out the applications highlights 3D printing of low-loss RF devices talk today. My name is Phil Lambert. Check out our website at 3dfortify.com to get access to more information on these awesome low-loss materials, and check out some of the other tech talks. Thank you very much.